I want to ask you to do a 2-minute pitch to investors. Why should they care about Kothar Computing?
What I would say is that the future of computing and the future of technology is quantum. The most important barrier to building quantum computers and quantum technology today is strangely still on the classical computing side. Eventually it will jump over into hybrid computing, but for now it's the classical computing side. The quantum electronic design automation stack needs to be built if you want to push the community from scientific experiments to an industrial scale ecosystem solving real utility scale problems and realizing the full value of quantum tech. Kothar is the engine that allows you to unlock this. And the interesting thing about building the engine for quantum electronic design automation is it also double functions as an absolutely fantastic engine for the future of hybrid quantum classical computing. Kothar is going to have a high impact in a lot of different communities, and we're going to fundamentally change the way that scientists and engineers interact with computing and the types of projects that they are able to do. And so that's basically my pitch. It's to disrupt and reboot scientific computing and quantum computing and unlock quantum computing, let's say.
Let's go to Aleph. What are the basics of Aleph? We touched already a little bit about it, but can you give maybe a short summary in 1 minute?
Aleph tries to draw things back down to the basics. It has 5 core, just like a technical detail, it has 5 core fundamental types. That is complex numbers, real numbers, integers, strings, and booleans, so that you don't have to think about that. Aleph is basically a language that's trying to mix symbolic computing with numerical computing, high performance computing without any overhead. So typically these two things exist in separate ecosystems. So you can think of the great 90s success scientific computing software, Mathematica and MATLAB. If you're in one space, you don't have symbolic computing, and in the other, you don't have good numerical computing. We're trying to do both in one ecosystem, which is a distinct power of Aleph. It's as easy to type as Python. There's a little bit more stricter rules around type safety and other things like this. But if you're programming well, you won't notice these rules because you were probably following them by accident in Python. Anyways,
you touched on symbolic, manipulate expressions and operators, and numerical, run solvers. Can you explain the basics to investors? So what is the difference between symbolic and how do you manipulate expressions and operators, and what are numerical run solvers, and why do they matter?
Yeah,
for somebody who's not familiar with it.
Yeah. So symbolic computing is like the computer doing math the way that a human would do math on pen and paper. So it's all about canceling common factors. It's all about looking at the expression and manipulating something that's just symbols, basically, right? So think back to high school or university math that you can do with pen and paper, but the computer is able to extrapolate those rules and do them on a scale that a human wouldn't be able to do. Anyways, numerical computing is what computers are really good at. It is representing things numerically as numbers, and then doing the vast majority of computation in industry is numerical computing. So it is multiplying matrices, it is representing your system with numbers and evolving it in time, etc. So it's the workhorse of the algorithms. Kothar is dedicated to making those two ideas coexist because it's a necessity to make them coexist in the quantum context. There's so much structure that can be exploited in quantum many-body problems before you commit to the numerical task. If you don't do the reductions that are available to you, you're talking about 100, 1,000x more complicated problems. So the symbolic part of the code might prep your problem, and then the numerical part of the code solves the problem. That's the idea.
Okay, thank you. If you had to, what is one workflow where doing symbolic, numerical, and performance tuning separately is a mess, and what changes when they're integrated in your stack?
I'll talk about how you can break the limits of an algorithm by mixing, or a limitation of computation by mixing both of them. And so we have a tutorial on our website about this. And the idea is, and hopefully you'll let me be a little technical here, but basically The idea is that when you're committing to numerical computing, you have to pick the quote unquote picture that you're in quantum mechanics. So like something fundamental about quantum physics is that there's really no difference between the the state of your system time evolving or the operators that you want to measure and having like sort of their configuration time evolving. Or there's also pictures where they kind of both do at the same time. And it's kind of like this is a question you can ask. Now, if my problem doesn't have what are called symmetries, and like let's say I'm limited to a laptop with, or like let's say I'm limited to a computer with 128 gigabytes of RAM. So this would be like a medium-sized workstation for someone doing scientific computing. Then, if I wanted to account for all quantum information in a problem, fully exact, then I am limited to only simulating 32 qubits. Whether or not that's doing it with a quantum circuit, emulating a quantum computer, or I want to do real-time evolution as if it was a real material doing some specific physics. The story changes is if you have symmetries and there's some symbolic ideas there, but we'll skip that part. If people want to learn about that, they can go to our website and deep dive the docs. But what you can do instead is you can say, okay, well, at the end of the day, I want to measure the expectation value of a specific qubit. I want to know what it's doing. And that's all I care about. And so instead of time evolving the state where I'm hard blocked at 32 qubits, there's a lot of ways to break past that barrier, but one such way is to go to symbolic computing first. And what you do is you just use the algebra of the thing that you want to measure and the Hamiltonian that's responsible for the dynamics, and you just evolve that. And so there is a memory problem as you go deeper in time because the expression gets bigger and bigger and bigger and bigger. You use the symbolic engine to compress and cancel terms as you go because terms start repeating and all of these things. You can also throw away terms that are getting too small. But basically the idea there is that all of a sudden I have unlocked the ability to do something like, 60 qubits, 100 qubits, basically an unbounded amount, and my time now becomes how far into time can I go, rather than how big of a system size it is. It's how far into time can I go. And the thing that brings us back to numerical computing is now I have these big expressions, and now I need to compute something about that expression, and you offload that to a numerical solver. You say, I began in this state, and now I want to bring that into a like an expectation value, or I want to study something about the system, and that's very simple. You just throw that into one of our numerical solvers, and we can handle that incredibly large increase in size with a couple of specialized routines.
Okay, thank you for explaining that. And I want to switch gears a little bit. I want to dive into the quantum EDA angle. What excites you about quantum EDA, and can you describe your vision and the basics of quantum EDA?
The thing that excites me about quantum EDA is that I think that this is the most important scientific computing task humanity is facing right now, because we're pumping billions of dollars into the quantum industry. And like, I don't want to be provocative, but for all intents and purposes, we're still at the scientific experiment layer. This isn't an engineering field. This is an industrial scale industry. And part of the reason for that is that the EDA tools that come from the classical space, they're not actually capturing. So
like Synopsys and Cadence, you mean?
Yeah, Synopsys, Cadence, Ansys, these types of folks. Those tools are not designed to capture the quantum physics that go into these devices, right? Like at the end of the day, the most important components of those devices are quantum components. And so in some sense, the tools that people are using to design these chips, they run some simulations on software, and then they go hand it over to a fab, and they, you print off your chip. In the silicon and superconducting case, they are blind to the types of physics that actually will give them like their industrial relevance, right? The quantum components aren't actually being modeled, right? It sounds silly. It sounds silly, right? But like that's basically what's going on, and we've made frankly incredible progress by not modeling the things that are the core drivers of the value of the technology. And if we want to turn this from a scientific experiment that it's going really well. Like, getting into the hundreds of qubits, it's remarkable of where we've come. But fundamentally, you want to turn this into a community that can boot up a top to bottom a simulation suite that can just allow an engineer to go in there and try new ideas and figure out how they want to design their quantum chip that fully captures all of the physics that matters for the technology that they're designing. You want to stop the problem of them being basically blind to blind is maybe like a too harsh of a thing. There's lots of things going on. There are things that we're capturing that are important. But at the end of the day, like if you're not fully modeling the physics that you care about, you're missing like a large amount of things that you should be aware of before you commit to going into the lab.
Can you explain the benefits of the partnership with Nano Academic Technologies?
So Nano Academic has a really unique product. It's called QTCAD. They're also lovely people if you ever get the chance to meet them. And basically what they do is they start from the bottom and they go up. They construct realistic models of your chip. And there's a lot of like semi-classical problems that you have to solve. There's lots of things that look like the types of things that they're doing unique things. They have lots of innovations, like specializing the software so it can accurately model the physics at the temperatures. Even that context, like that's a hard problem, and they've solved this problem. And so what they do is like they basically construct the realistic models for you, and then our partnership is basically us being the engine for once you get to the quantum many-body context. Eventually you model the chip up to the point where you can accurately build either a high resolution equation for individual qubits or a handful of qubits, or maybe even a more zoomed out picture of the chip, and then it's our job to solve those equations basically. So we provide the last layer engine to be able to solve the hard quantum many-body physics problems, and then our goal in the next like 18 months is to get that to a point where we can model 100 qubits at a time for hardware manufacturers.
Thank you. What does TCAD bring that quantum teams lack today?
What does like QTCAD or
Yeah, TCAD. How do you pronounce
TCAD?
it?
Oh, like just regular computer assisted design.
Yeah.
Well, I mean, it's in some sense it's like a very simple answer, and that is you want to be able to model things before you commit to expensive lab or fab runs. And so getting like people, when you talk to folks in a variety of contexts, it's like I want to be able to model this before I commit to doing something expensive. And the community right now doesn't have a lot of tools like that. Like when you're talking about like photonic interconnects, when you're talking about different, even quantum sensors, like those folks don't have tools. Like that's a big benefit. And then I guess the other benefit is that like these people don't want to make these tools themselves, right? Because it's a completely different skill set to want to build quantum hardware than it is to simulate. So getting an accurate picture of what they're about to do before they do it, that actually matches what they do in the lab once they go and look at it in the lab is the big benefit.
Can we talk a little bit about the workflow of a chip designer? What do they input and what do they get back? And how will it change in the coming 5 years?
Yeah, I think so. Right now they're chaining together a bunch of maybe disjoint tools. There's not a complete vertical integrated stack that can go from this is the silicon system that I want to put my chips that I want to build my chip on, all the way to this is what I want you to print out of the fab, and that's kind of like the status quo today. But I think in 5 years we're going to be looking at a like at an ecosystem where you can go from fundamental design choices all the way to getting a file that you hand off to a fab in one vertical integrated workflow. I think that's where we'll be in 5 years.
Okay, thank you. Spin qubits versus superconducting. What differs in modeling the pain points, and what is surprisingly similar?
Surprisingly similar is kind of the thesis of Kothar, and that the fundamental tools and building blocks for the software are identical. The moment that you specialize the fundamental physics, though, like once you specialize the tools, is that they're very, very different. So in quantum dots, you have an electron in a cavity, and its spin is what's providing the qubit for you. And it's not like that in the superconducting a qubit case. You have a completely different physical model, not only from just the physical model of the qubit, but then also when you zoom out and the effective model of the chip itself is different. But so fundamental tools, building blocks the same. The fundamental physics is different. Is my answer.
Okay. On spin qubits, one of the disadvantages is it could potentially be a dark horse, but the accuracy is still low. What is
Yeah, I would say they're yeah.
how can you help with higher accuracy?
Higher accuracy. I mean, here's the interesting thing. I do think that they're the dark horse technology. You can pack more spin qubits into a smaller space. They're going to have less of a scaling issue. I think the higher accuracy is really going to come from the fact that this community is going to be the first one with a full quantum EDA stack from software simulation to like not to plug Kothar's tools and really to plug our role in the ecosystem. But I think at the end of the day, spin qubits have the advantage of being very closely connected to the types of technology that enable modern classical chips, and they will be the first ecosystem that's able to adopt a top to bottom full quantum EDA suite from manufacturing the chips to modeling the fundamental physics of the chips. All of that will be captured in the next year and a half.
Why is that? Why do other modalities don't have that?
It's really how new the technology is, right? Like it's the question of do you adapt existing technologies to try and innovate the new wave, or do you try and do something radically different? And spin qubits are not radically different. They're very similar to, I mean, it's wrong to say they're very similar to classical chips, but they're the closest thing. Like the adoption and the industrial momentum is there. They just need to catch up to the rest of. I think that it's a little bit elusive. Like for any investors that are out there that haven't really decided which horse to bet on, like I would say that the total qubit count is kind of like that might be the wrong thing to be looking at. I know it's fancy and I know it looks really cool, but like you can have 1,000 qubits and not be able to compute anything interesting that Kothar's classical tools can't. It's really about the robustness of the qubits and the type of integrations that they'll have with interconnects to classical HPC, like basically every detail that can go into the chip is going to matter, and so I think spin qubits are a real dark horse.
Okay, clear. And I want to talk a little bit about IP and coming back to barriers to entry. How hard is it to copy Kothar Computing, and what is the hardest part?
Yeah, so I mean, it's an interesting question, and it's a thing that we always come back to, and like how you actually want to position yourself, because at the end of the day we're a software provider. We write code, and the way that folks have tackled this issue in the past is really different, right? Like you can go the MATLAB route and stay fully closed source, and you can basically fully integrate yourself in a way where like adoption would just be a nightmare if you tried to directly compete with MATLAB, and that's one way to protect your IP and your position in the market. Another solution that you can do though is you can basically make it so that there really is no benefit to competing with you, right? Like you have like the Red Hat model, you have open source models, and then you have monetization around open source models. Yeah, like there's strategically, I would say that Kothar hasn't picked a path per se. I think there's a lot of the stack that probably should exist in the open source regime, and then there's a portion of the stack that's very industrially relevant that will stay closed source. And that will be more about protecting it through adoption and stickiness than it is about filing patents and protecting it that way.
Can we talk a little bit about the talent pool and the locations that you have?
Absolutely.
And why did you select the current location, or why is the current location the best one for you?
So Kothar has very, very, very specific needs. We need physicists that can write good quality code, not the physicists that will tell you that they can write good quality code, the physicists that can write good quality code. And so there's two corridors in Canada. So one, I'm Canadian, and that's one of the reasons why we're here. There's always the pressure as a Canadian to go down into the States, into one of the major tech hubs, like San Francisco, New York City, Boston. But there's two corridors that are really exciting in Canada for quantum tech and the type of talent that we need to that we need to generate. So the first corridor is Montreal to Sherbrooke. So McGill University, Institut Quantique in Sherbrooke. These are two fantastic corridors. In fact, I would say it's probably the biggest, best untapped market for talent because other quantum companies are not setting up here and they're not hiring here. A more competitive market is the Toronto to Waterloo. So between the Perimeter Institute, Institute of Quantum Computing in Waterloo, to the University of Toronto and everything in between. This is like basically Canada in those two corridors that are a 6-hour drive away from each other supply all of the talent that we could possibly need. And then there's also there's other location benefits from a business development perspective that Canada is quite good at.
Okay, thank you. That's clear. And what IP do you have?
What intellectual property?
Yes. And what part is significant?
The fundamental IP of Kothar is we wrote every piece of code from scratch because the infrastructure just didn't exist to start somewhere else. So the entire compute engine for quantum many-body physics, that is our primary IP, and then building up the software ecosystem around it. So we have our programming language Aleph, we have all of its functionality internal to it, so the quantum many-body physics engine, and then we have our web-facing app called the Workshop, and that's like the Google workspace of scientific computing.
That's clear. Can we talk maybe, we talked already a little bit about it, but maybe summarizing or what is the value for customers? And what product and services do you offer?
The value for customers is taking a 12-month long project and compressing it into a week. So it is and allowing them to do more ambitious problems. So it is removing strain on software orchestration, getting them up and running, orchestrating all their hardware together. Like one simple task and never having to touch that again, and then it's giving them a platform where they're going to write code that's 1,000 or 10,000 times faster than what they would have written on their own in a way that's expressive and allows them to solve the problems they care about.
Why is it 1,000 times faster? Because that's quite a bold statement.
Why there's algorithmic and infrastructural advantages. The algorithmic ones are, you can think about it as just significantly reducing computational complexity or the size of the problem internal to the algorithm. And the infrastructure one is like one example would be, when and why do I have to allocate, like Kothar is really great at what are called matrix-free methods or like easy typing to construct problems. And in the exact diagonalization space, I apologize for getting technical, like the key component there is that you basically never allocate a matrix. It's all matrix-free. It's all symbolic expressions interacting with numerical containers like vectors or whatever.
And Jonathan, why does it matter? That's matrix-free and that's symbolic and numerators interacting with each other.
Why does it matter?
Yes.
So one is it reduces the memory overhead significantly, so you can do larger problems. And two, it's very surprising. This isn't what even some of the developers internal to our team thought was that the alternative is to load something into a matrix, whether it's dense or sparse. And the question is okay, if I do it symbolically or if I do it from a sparse matrix, which one's going to be faster? And the answer is that doing it symbolically is orders of magnitude faster than the sparse matrix. So you basically construct expressions that internal dispatch to our custom infrastructure and kernels, and those are significantly faster than codes that you would write in other contexts that are very common in the community.
Clear. Can we talk a little bit about the business model, how you monetize it?
Yeah, absolutely. So for academics, it's basically our priority there is market penetration and adoption more than it is revenue at this stage. So it's basically pay as you go. So if it costs us money, it costs you money. And so resources that you use will cost you money. And that's currently like the status of things. And then when you're talking about,
Jonathan,
to give you examples.
Can you quantify it a little bit? So what does it mean? If a university wants to use Kothar Computing, is it subscription based? Is it license based? Is it like for one university you have one license, or is it per person, per seat, or is it a combination?
It's per seat. So if you're an academic, you go to our website, you click sign up. Currently we're in closed beta, so we'll take you if you're very relevant and we think you're going to give us a unique perspective. And internal to that, like there's mechanics to that in the sense of you have your own license, it's your seat. If you use our cloud computing services, if you use our AI agent, or you use our cloud storage, that costs you money. It's basically a markup in what it costs us. So it's like token based. It's basically like it's almost like ChatGPT or Cursor or any of these things. Based off of the conversations we have, because of the nature of academic research, that means a customer might pay us $200 a year, or that might mean a customer will pay us $20,000 a year. It's not based off of cloud compute resources and things like this. It depends on how they want to interact with the system. There will be a license for universities if they want to come in and set up and integrate their compute infrastructure with ours, so that the customers that are from their university want to integrate with their compute resources. Then that's kind of like an individual contract situation where we discuss with them and integrate, because there's a whole service aspect to that. And then when you jump over into enterprise, that's really where you get into specialized packages for people that have specific problems that we need to specialize our software for. And then that business model is basically identical to Synopsys Cadence. It's just adopting the industry standard of you're paying for an EDA software, it's per seat, and depending on how many seats you have, and depending on how integrated you want us to be with your compute ecosystem, and how much you want us to orchestrate it, the cost will be different. But those enterprise licenses, the standard would be let's say 50,000 a seat or something like that.
What about business momentum? Can you walk us through customer adoption? And do you have concrete data points that prove that there's demand for the solutions?
So customer adoption. So we have a fair amount of people on our waitlist. We haven't really been advertising at all, so we're a bit earlier than I think this question probably wants us to be. So our closed beta, we've let in, I think it's 130 now. The marketing effort to actually bring people in hasn't begun. The proof point that we feel is very strong is that there's two proof points. One is that on the enterprise scale, these are problems that people are asking, Nano Academic to solve. And there are problems that they very clearly have to solve to build quantum computers at scale. So that's a good place to be. And then on the closed beta side, you have users that are from very different communities, very different fields, fundamentally committing to long-term projects with the tool. So we think a concerted marketing effort will bring in, let's say a couple thousand users by the end of the year once we begin it.
So that's a good start. What are the main drivers for future demand?
From the enterprise perspective, I think a lot of quantum computing startups, our value in how much demand we're going to get is really going to scale with the quantum computing industry. The larger the chips get, the more complicated the quantum sensors get, the more people are going to need to be able to solve these tools at a scale that only Kothar can currently solve them. And so that's where that demand is going to come from. The demand from academia is, Europe has a very healthy academic ecosystem. There's a lot of physicists solving new problems. Those problems are never going to go away. It's not, this isn't a civilization game where the tech tree runs out. We still have really big hard problems. And the more we spoke to folks at a space agency where they're worried about that these are mechanical engineers, material scientists that are mostly used to dealing with classical physics problems. But the more and more you design these machines, these technologies at different scales, eventually you're going to have to care about high quantum correlation problems. So they're worried about micro fractures in material and then hydrogen leaking out of that material. Well, guess what? That's a high quantum correlation quantum many body physics problem. And so basically the trend in humanities technology is that Kothar is going to become more and more relevant as we scale. We're seeing it now. People need these tools now, and then they're going to need them even more in 10 years.
Okay. Can we talk a little bit about the management team of Kothar? And can you walk us through how the team came together and why are they excited to work on Kothar Computing?
The punchline for why everyone's excited about it is this is answering a deep pain point that we all experienced going through our PhDs. So we have 8 full-time equivalent folks on the team. So we came together initially, I was working on this on my spare time. one of my co-founders, Sebastian Avakian, he messaged me one day out of the blue. He was a master's student when I was a PhD student in the same group at McMaster, and he was like, "Hey, why hasn't anyone built this thing?" And it was like a subset of all of the things that I wanted to work on, and I was like, "Well, I'm currently building this. Like, do you want to come and work on it with me?" And then we started to sort of talk with our the people that ended up being our first investors. At first, it was an innocent conversation. It was, what license do I put on this so I could keep my option open to build a business around this in the future, or make sure that this is free for academics, or no one else could build a business around it, basically. And that conversation became, what does this have? What does this become if it gets resources? And that's how those conversations started. Another one of my co-founders, Edward, he's just a good friend of mine, and he was listening to me talk about how difficult scientific computing is for a lot of people, and we would talk about it quite often. And eventually, he was a front end developer, and he basically said, like, why don't you let me build, like, this can't just be something that is on the command line, right? Like, that's not actually solving the problem. You want an actual app. Like, what does that app actually look like? And we started talking about that, and then he started working on that, all of us doing this for free at the beginning. And then our last co-founder, Alexa, came to us through our connection with the investors. She came in for the business development side, and we started the company in August 2024, basically, with that roster. And Alexa was excited about it because she was consulting with me with Cinead when which are our initial investors, when they were forming their quantum tech thesis. And it was clear to both of us that the future of quantum computing was hybrid computing. Like, the classical stack needed to be developed. And so from a tech vision, she was very aligned. And continues to be very well aligned. And then we were able to we headhunted every one of our employees. It was, okay, I need an expert in tensor networks. Okay, who's available between Waterloo in Ontario to all the way to Sherbrooke in Quebec? And you go through, you find the best person for that. You ping them and you say, hey, I'm building this thing. Would you want to be a part of that? Would you want to come in for an interview? And the answer is yes. And then you go through and I think the interesting thing about physics is that the culture internal to physics departments is pretty universal. We might speak different languages, we might be in different countries, but there are differences here and there. Like, it's a really easy fit when you have physicists that are really motivated and excited about a problem. And so we went through and headhunted the rest of the team, picked up the specialties that we needed, and that's basically where we are.
And what do you mean with headhunted? Did you hire a headhunter, or was it the team self that you on LinkedIn?
We headhunted ourselves. We knew about, like, our lead high performance computing person. We had heard that he was one of the best people on the island of Montreal, and so we reached out to him and said, hey, are you happy where you are? That's basically, like, just finding out who we thought was the best and then reaching out to them. Like, I think we didn't really accept resumes. We reached out to people that we wanted to join the team. Some people said no, and some people said yes.
And how did you figure out who was the best in that specific capability?
Basically pinging our network. Do you know anyone that's good at this? Going into specific institutions, seeing who's working on what, looking at their publication history, all of that. Like, it's a very interconnected community. So, like, for example, folks at the Perimeter Institute, I know a bunch of people there. I pinged them and I said, hey, who's the best at this right now at the institute? and then you go and ask that person if they want to join.
Okay, that's cool. How do you scale the organization, Jonathan, from a startup to a mid-cap?
It's an interesting question, because this is something we're internally talking about as we raise capital for Kothar, and we want to expand the team. And that is that right now we have a team where it's basically a flat structure across the development scale. People have ownership over what they're working on, and they're the leaders on their projects. And then we have, like, de facto leaders that you defer to in a lot of contexts. And the flat structure is really attractive because there's basically no bureaucracy. There's just a team of people that get together and solve the problems that they're naturally excited about, because that's the problems that they were hired for. And I guess the answer is to a team like Kothar needs to be built out more on the business and hiring more, again, division of labor. You want folks to come in with more, like, a background in an MBA, experience in other deep tech fields that can bring the business side expertise. But when you're expanding the technology side, you're also talking about, like, using your existing team as kind of like, a core leadership team, and then growing the team underneath them. That's the way that we're thinking about it.
Okay. Can you walk us through the culture of Kothar Computing? And what defines the culture of Kothar Computing and how does it relate to your mission statement?
Yeah, like one of our mission statements is like simple is better. That's a core design goal of Kothar, making people's lives easier. And so I would say that the way that we accomplish that is a really good credit to our culture, is because at the end of the day you have 8 people, on a Google Meets, and we have a very good culture of, I'm just going to say what I don't like about things. I'm going to say that I think that this is that we should design this differently, or that. It's a very open environment where everyone understands that they themselves are not being criticized, and we're just trying to get to the best solution. So it's a very collaborative environment. It's a very open environment, basically, and that's the culture. That's the culture of Kothar. Everyone really cares about, unintuitively, if you come from other ecosystems, but everyone cares about the speed and performance, and at the same time the elegance and ease of use of everything that we build. It's a huge, everyone's really embraced the vision and really pushes to make sure that we stay on vision and on quality, and everyone feels comfortable doing that. So giving people ownership, I think, is key to unlocking that type of buy-in.
Can we talk a little bit about financial targets? How do you estimate the total addressable market?
The total addressable market is an interesting one because you can look at Kothar in from two angles. The first angle is, how many people in academia in different fields can you get this tool to, and sort of change their workflow. And we think that answer is, in the next 3 years, like about like a little bit over 100,000 people. And I think the difficulty of like actually understanding how much you might make in terms of income from these folks is difficult, because every budget is basically different. Like how people get grant money, what they can spend it on, how fast we can integrate with those grant cycles, etc. But you can start from there, in terms of how many people that you can actually get this to. In terms of industry, there are a lot of places. It's actually difficult to pick the directions that we want to take Kothar. So for example, I think between quantum sensors and quantum computers, there's probably like 160 hardware companies, I believe, if I'm
Mhm.
if I'm counting correctly. I might be double counting, to be honest. But then, like, if you look at those companies, there's like, to build up the addressable market, you're thinking, these folks will have 5, 10, 20 simulation people dedicated in-house. They'll pay X amount for the software, let's say 50 to 100,000 per seat. And that's kind of how you build up the like the addressable market from that perspective of, how much money could we actually make in each ecosystem. And it's not just those ecosystems. The difficult thing about Kothar is people are trying to build novel RAM and novel transistors with quantum many-body physics.
It's a
Type,
huge
that
topic,
type.
Innovation in memory nowadays.
Yes,
With the
yes,
HBM
and so,
memory.
yeah, and so, like, the answer is that, like kind of like the sky's the limit. I think Kothar is, like, early days. I think it could be like we're going to be a high income earner, but like long term, I mean, like, are we, not to toot our own horn, but like, are you looking at like the synopsis of like, are you looking at an early synopsis in 1988 or something like this? Like the new technologies, and the amount of companies looking into this, and the amount of money being put into these ecosystems is incredibly high, and it keeps growing. So that's another difficult thing about total addressable market is, what's the market going to be like in 5 years? I don't know if people predicted this craze over compute 5, 6 years ago, right? But is the craze over compute going to slow down? I don't know. I mean, there's people that definitely think it should, or it has to, but then there's also companies that are buying, certain RAM manufacturers are bought out for the next 2 or 3 years. So at least in terms of financial commitments, I don't think it's going to run out for the next 3 years. So yeah, I guess it's a difficult. It feels like sky's the limit. It feels like a difficult. It's always a difficult thing to quantify for us, because there's the reality of today, and then there's predicting what's going to happen in 3 years in the most important. Like, if you take computing as a whole as the most important industry on Earth right now, then yeah, I mean, who knows what's going to be happening in the industry in 3 years?
Yes, I agree. Jonathan, when will your conviction on Kothar Computing increase?
When will my what?
When will your conviction increase?
Conviction or
So maybe give a bit background. As an investor, for me, sometimes you have two companies, both have
yeah.
20% upside, but in company A, I have higher conviction than I have in company B. Maybe company B is more binary.
And can you define that word? Like what do you mean by it?
The probability for success. So when would the probability for success for you go up? What are you looking for? You say, well, if this happens, then I'm convinced we succeed. What are you looking for? Or what are the key points for the coming 5 years? You say, if those things happen, then my conviction goes up that we succeed and become a standard.
So the thing that I would say is instead of saying 5 years, I'll say the next year and a half. That's the time period that I want to bet on. And in those cases, growing the user base to a few thousand people and becoming a mainstay in the quantum EDA stack and having widespread adoption in the platforms that we want to service. Those are the key indicators that I would give to have us be a high probability player for the next 5 years, 10 years.
And why did you pick the amount 1,000? So could you walk us through? So why 1,000 and how do you reach from 100 proof of concept, closed beta testers to 1,000? Can you bridge that gap for me?
Yeah, so I'm talking about thousands. And when I say thousands, I'm talking about having a community. I mean, for one, I want to set a realistic goal, but two, I want to have not thousands of people that have accounts. I want to have thousands of people that are actually using the tool and the platform. And by that, if you're talking about thousands of people using it, you're talking about probably like on the order of like let's just say several research articles being published every week that's citing us as a primary tool. And like that's a natural place where now we have a foundational community that's not going anywhere, that's using us to grow. And I think that that's the point where instead of it being a fight to continue growing the user base is going to start growing itself in the sense of people are going to be building tutorials based off of us. We're going to be more of a culture component of physics and R&D rather than the new kid on the block that's trying to get you to try something new. At that point, everyone knows that we exist, and it's just a matter of time before we get them.
Okay. How much capital do you need? And what can you achieve with that money?
Yeah, we're currently looking to raise 4 million US. There's two core goals with sorry, I guess there's three core goals with that money. One is so right now we're basically a deep tech team. Our Myself as the CEO, we have one of our co-founders dedicated to business development. I do business development, and everyone else on the team is dedicated to R&D. We've proved that the new direction and the new technology works. There's distinct advantages. Now it's time to monetize it, and now it's time to market it, basically. So we have the POCs, we have the initial users, and basically the money is being used for exactly what I said. It is to hire the right staff to go out and monetize it, build relationships with the quantum hardware manufacturers, make sure that they have what they need. It is to market it. So I think one of the things that I really like, or like to compliment someone else in the industry, it's what IBM has done around Qiskit and the ecosystem that they've built around Qiskit in the sense of YouTube videos, marketing, etc. The Qiskit Advocate program, for example. Kothar needs like all of those things. I make YouTube videos when I have time. I do not have time as the CEO to make like realistically a marketing campaign looks like us posting 5 to 10 shorts a week. It looks like us posting 2 long form videos a week, several LinkedIn posts, being extremely present. And it also involves creating more learning material for people and having a primary point of contact that's reaching out to people in the community, getting new people on board, etc. So that marketing arm needs to be built. And then finally adding more to the deep tech team so that we achieve our goals and we can service the communities that we want to service.
Okay, that's clear. Thank you. Can you walk us through the positive flywheel and why can you innovate the fastest? And why are you the best long-term solution?
Like it's like at the end of the day, it's about getting the right people solving the right problem. I think our like if you really buy into our tech vision, you'll realize that it is extremely unique compared to what everyone else is doing. It's disruptive, and it's in a direction that I think the community has to go in eventually. And I think we have the right talent density and the leadership on our team already driving towards that. I mean, in a year we went from basically nothing to a functioning orchestration platform that completely abstracts away software like installation, coordination, etc., a programming language, a framework that captures a number of different quantum physics fields. With just a little bit more resources, we're in a position to cover way more areas in quantum hardware, quantum technology, hybrid computing, different communities in quantum physics. Like it's I think the success is already on the table if you accept like the ambition that we started off with and where we've arrived after a little bit over a year. Like we started in August 2024. We didn't have the team until November, December 2024. So we're a little bit more than a year into this, and we're already where we are, which I think is it's a really good a good proof point of that we'll continue this velocity. That's the
Jonathan, I really want to thank you for your time. But before we stop, there's one more question on top of my head. Do you have enough time for now?
Yeah, sure, why not?
One thing that fascinates me, and that is when I started a podcast, and that was October 2024, then the CEO of NVIDIA said, on the shift in compute from CPU towards GPU, at that point of time, the question was, will GPUs take over from CPUs? And will the workloads migrate? So CPUs will not disappear overnight, but will people, with a GPU, you can accelerate workloads. But at that point of time, there were not good enough algorithms, or not enough. But what Jensen said from the NVIDIA, he said, if you have the lowest cost of compute and if you scale most, you will get smart developers who will come up with new algorithms. How do you see that for quantum, and what is the role that Kothar can play with that? With enabling researchers and smart developers with new quantum algorithms.
Yeah, I think algorithm design is really a matter of, in some sense, it's the tools you give people to actually reason with and abstractly think about the devices that they're interacting with. One of the jumps that I think of is like going from assembly to C. You're not going to build your Chrome browser with assembly code, but you might build it with C++. So it's the abstraction layers, and it's allowing for you to reason about the hardware in a way that actually promotes specific types of reasoning that allows you to create different algorithms. And this is, in my opinion, one of the strengths of Kothar, is that it has a fundamentally built-in thesis for how hybrid computing should behave, in terms of, you should be able to write fundamentally complex classical blocks and quantum blocks in the same code and allow them to interact with each other and give feedback to each other. And so I think that like that punchline is, or like that observation is like fundamental to Kothar's vision, to give these smart algorithm developers the tools to actually innovate. They shouldn't, I mean, in some sense, in some contexts, they should be worried about what hardware they're running on, and in some contexts, it should only matter that it's a quantum computer that they're running on. And then there's going to be other contexts where, the fundamental, the fundamental structure and compute model of a GPU is the only thing that matters. The actual instructions and specific things that you can put on it shouldn't matter. That should be our job, to make sure that you can reason at the right abstraction layer to write new algorithms. And so that's a hole that I think Kothar's filling as well.